Bam, Mr. Taru. In this video, we're going to take a look at the summation notation, this Greek E symbol here, which basically just means repetitive addition. This notation can be found in a lot of formulas related to finance, where you're talking about money. Maybe it's the total loan value or total income from an investment. You'll also see it in many probability question or probability formulas and formulas that we use in statistics, because statistics is basically mathematics that is based off of the study of probabilities. Now in pre-calc, we are just going into the topics of sequences and series, and that's how we're using this notation. So we're just going to do a basic introduction of the notation, show you how it's repeated addition, and then do a couple of examples where I give you the summation notation, and we are going to come up with the terms in a sequence. And then we'll give you a sequence of the values and then ask for or try and figure out what the summation notation expression would be that would give us a pattern. So we got this Greek E letter. It'll be to the left of some kind of algebraic expression, and we have this index I. Now it doesn't have to, you don't have to use the letter I. You can call it N, K, whatever letter you like, but there's some kind of index, and I is called the index of the summation. The N, this number at the top of the Greek letter, is the upper limit of the summation, and 1 is the lower limit of the summation. Now, I'm writing this pretty much as my book has it. However, it's kind of, the 1 is just really here in the general standard form. The lower limit really can be something, another integer other than 1. Just remember that this is the lower limit and this is the upper limit, and we're going to increase what we count by, we're going to increase it by 1 until we get to the upper limit. So what you're going to see in the examples here in a second is there'll be an expression here. Whatever this lower limit will be the first number that we plug into this expression, and in this case it's 1. I would plug 1 in, I would get a term, and then increase it by 1 and plug in 2 to this expression to get the second term, and then I would plug in 3 into this expression to get to the third term, and so on, and just keep plugging numbers in, getting bigger and bigger by values of 1 until we reach the upper limit of n. That would be the end of the sequence. So you could have an infinity symbol up here, but most of the time you're dealing with finite sequences, so there'll be an actual last number in the sequence, and then you'll go back, and the Greek letter now comes in, the summation symbol comes in, and you're going to take all of those terms that you found and then add them up and find the sum. So let's get to some examples. Bam! So we have our 3 examples where we're given the summation notation, the expression, and we're going to work out the sequence, the finite sequence of numerical values, and then do what the summation symbol says, which is go through all those values you just found, add them up, and you're done. It's just new notation. The mathematics are pretty simple. We're just going to do a lot of substitution and a lot of arithmetic until we find the sum. So we're going to take this expression of 2n squared minus 3. We're going to start plugging in values of 1. We're going to increase by 1 until we get to the upper limit of 4. So we're going to have 2 times 1 squared minus 3. I'm going to wrap this in parentheses just to highlight each individual substitution. They're not really going to do anything except for, well, just to do that. Highlight each substitution. We're going to plug in 2 and get 2 squared, or 2 times 2 squared minus 3. And then we're going to plug in 3. 2 times 3 squared minus 3. And then finally reach our upper limit of 4. So 4 squared minus 3. All we got left to do is a little bit of arithmetic and find the sum. 1 squared is 1, and 1 times 2 is 2, so we have 2 minus 3, plus 2 squared is 4, and 4 times 2 is 8, plus 3 squared is 9. Don't forget to do your exponents first, right, before you multiply. So 3 squared is 9, times 2 is 18, and then 4 squared is 16, times 2 is 32, minus 3. So we have 2 minus 3 is negative 1, 8 minus 3 is 5, 18 minus 3 is 15. And 32 minus 3 is 29. I think by now I probably could have just dropped those parentheses, but I was rolling. So we've got 5 and 15 is 20. 20, another 20 makes 49. Well, I'm thinking of the answer. Let's try that again. 5 and 15 is 20. Now it's 40. Now it's 49. Minus 1 is equal to 48. And that's all you have to do with the summation notation. Plug in the values, go from the lower limit to the upper limit by just simply increasing your substitution values by 1, and do a lot of arithmetic. Now here is a couple of special cases. The summation of k factorial over 2, or k over 2. And factorial, if you're not familiar with it, I'll explain it as I go through the problem, but I'll have a full video about factorials right after this one. I'll make one. And we have a lower limit, upper limit, and just like the first example, we're going to plug those in. So we have 3 factorial over 2 plus, now upper limit, I'm going to increase by 1 and I'm done already, 3 to 4. So 4 factorial over 2. Now again, if you've never seen a factorial symbol, the factorial tells you to take a positive integer, and that's what you're allowed to plug in. And you count down by 1 until you get to 1, and then you multiply. I guess actually for the, on a number line it would be what? Yeah, count that by 1. Okay, so 3 factorial is 3 times 2 times 1 over 2, plus 4 factorial is 4, 3, 2, and 1 over 2. Cancel anything out just to keep the numbers a little bit smaller. So 2 divided by 2 is 1. And again, 2 divided by 2 is 1. And we have 3 times 1 is 3. We have plus 4 times 3 is 12. And our final sum is 15. Make sure I got that right. Yes. I'll cover this in my video about factorials after I step back in the screen here. I'll cover this in my factorial video, but just as a verbal note, with these factorials, 0 factorial by definition is equal to 1, in case you happen to see that in your summation problems. Now this last example here, we have the summation of 4 with the, the index values of 2 to 5. So we're going to find the summation of 4 with using the n values of 2 to 5. Well, you might be going, well, this example and this example gave me variables, to plug in these index values. I had a place to plug in my 1, 2, 3, and 4. I had a place to plug in my 3 and 4 in for k. This is a constant. This value of 4 is never going to change. The expression is 4. It's a constant. So what am I supposed to do with 2, 3, 4, and 5? Well, that tells you how many terms that you're going to have. Let's use the index value of 2. Well, where am I going to plug it into? Nowhere. But the expression, the value of this expression is going to be equal to 4 when n equals 2. Well, now n is going to equal 3. What's the value of this expression? It's still 4. Now the n value is going to be 4. Okay? Starting to lose place where I was here. N value 2, n value 3, n value of 4, and then finally an n value of 5. So I've still got 4 index values, 2, 3, 4, and 5. And we're attempting to plug them in to the expression, but the expression is a constant value of 4, so its value will not change, but it's still indicating that we have 4 of those 4s, so our sum is going to be 4, 8, 12, and 16. I'm Mr. True. Bam! That's how you work with summations. So now that we know how to use summation notation, how about going in reverse? Here is a sequence of numbers, finite sequence. It goes from 1/4 to 10 over 13. Express that sum using summation notation. Summarize it into a single expression instead of a long series of additions. Well, when you set up sequence notation, you are looking for, again, some kind of summation, you have a summation symbol, and we're going to make some kind of index down here, and we have a choice as to what we want to use as our lower and our upper limit. All we need to do then is come up with some kind of expression that will make these values based on some kind of index number. And we can start this with any value that we like. We could say that n is equal to, let's starting at 0, 1, 2, and then so on, and figure out what that last n value is for our last term, and go, well, how can I make a 0 into a 1 into a 2 into a 3, an n to a 10, and we'll scratch that last one there, that's just the upper limit. And then 0 to 4, 1 to 5, 2 to 6. Now this is a very, first example, and it's a pretty simple one. And I can very easily come up with an expression here. And actually, let's go ahead and do that. We'll just do 3 examples instead of 2. If I want my lower limit to be 0, or my lower index to be 0, then to get from 0 to 1, from 1 to 2 to 2 to 3, and, well, let's see. I'm taking my values of n and I'm simply adding them by 1. So, my expression would be n plus 1, and that will make all my top numbers, my numerators, out of these n values going from 0 to n. My denominators, well, how do I make 0 into 4, a 1 to a 5, a 2 into 6? Oh, all of these denominators are 4 units bigger than my index value. So my denominator is, well, just n plus 4. Now, what is the last n? What's the upper limit that I'm going to use in the summation symbol? Well, okay, this is my numerator, and I need my n plus 1 to equal 10. So if I take this and I subtract by 1, then I need my n value to be equal to 9. And just to double check that, I think this is going to be my upper limit. So just to double check that, let's see. n, okay, so 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. And if I let my 9 value be my last number, 9 plus 1 is equal to 10. And 9 plus 4 is equal to 13. So that is a correct answer. Now you might have been going, Mr. True, if you had just started your n values at 1, then this expression could have been, well, that's 1, 1, 2, 2, 3, 3. So my numerator would just be n. And my denominator, well, now they're just, now they're just 3 bigger. My lower limit, I've started at 1. My index and my numerators are a perfect match, so not only am I starting at 1, but n here, my upper limit, must be 10. So there's 2 possible answers for summation notation. Now if you just watch my video about my introduction to sequences and series, when you write an a sub n expression, we'll be doing a bunch of this when we get into our videos for arithmetic series and geometric series. But when you write an a sub n expression for a sequence or series of values, the n value must start at 1. Now, I'm not talking about that a sub n notation. I'm using summation notation, which gives me a flexibility on my lower limit value. That's probably why textbooks will default to using the letter I for index on summation notation, but half the time I write an I, it looks like a 1. So maybe I should have picked a letter like K instead of N to show some separation between that a sub n notation that I use. But just be aware that when you are given a list of values, terms, and you're asked for an a sub n expression, you do need to use your counting values. You need to remember that your domain is a set of all positive integers. But with summation notation, you do have a choice for that lower limit. So I didn't want to confuse you there. We have a slightly more complicated version over here, so let's go ahead and use a different letter for the index. Let's say that we have summation notation. We're going to let k be our index value. We're looking for a lower limit. We're looking for an upper limit. And then, of course, we're going to fill in our expression here. And let's just default here to k values of 1, 2, 3, 4, and 5. There's no dot, dot, dot with this one. I just went right to the end. Do you see any pattern between these k values and the numerator? They're all squared. So our numerator for this is going to be, I don't know why I keep making my box so small, but my numerator is going to be k squared, yes. I'm mentally checking my answer there. My lower index is equal to 1. With these summation problems, where you're trying to write an expression to match up with your series or sequence of numbers, make sure that you check more than just the first and second term, because you can sometimes and very commonly get a pattern, an expression that works a couple of times and then starts to fail. So don't check just one or two terms to make sure you've come up with a proper expression. Now, how do you turn a 1 into a 3, a 2 into a 5, a 3 into a 4 into a 9, did I just say 4? 3 into a 7, that's a difference of 4. 4 into 9, and a 5 into 11. It's a little bit tricky, so I'd like to pause here and see if you can find a pattern that matches all of these up. This is 2 bigger, 3 bigger, 4 bigger, 5 bigger, 6 bigger, so it's not just a simple addition. How about what's 1 times 2? 2 times 2. 3 times 2, 4 times 2, 5 times 2. If we double all these values, we're 1 unit away from this denominator. So, our denominator is going to be 2k, and then it was all just 1 shy, so how about 2k plus 1? And 5 squared is 25, so our upper index value, our upper limit is 5. And there's 2 examples of being given a sequence and asked to find the summation notation. I'm Mr. True. Go do your homework.